So what we're going to do today is look at the domains, at least part of the domains. And then we look at the variables, the constraints, and the propagation. So what is the domain in MiniCP? This is a set of integers. And so we're going to show you the implementations of these types of domains. There are other domains in constraint programming, but we are not going to talk about them in this set of videos. So this is the interface of a domain. It has functions to query the domain and functions to modify the domain, methods to query the domain, methods for changing the domain. So the first 5 are for querying the domain. The names really indicates what they do. This is for finding the min value in the domain, the max value in the domain, the size of the domain. This method here is to find out if the value v is inside the domain or not. You test if the value is in the domain or not. IsBound is indicating whether the domain is size 1, exactly size 1. So that means that there is only a single value left in that particular domain. So you'll see why this is useful, but a variable is, when a variable is a single value in its domain, we know that it is assigned, right? So that's why we have this isBound there. These methods here are for removing and assigning value. The first one is removing the value v from the domain. The next one is assigning the value v. We remove everything but v, so v is going to be the value which is assigned. Remove below is removing all the value which are below v. Remove above is all the value which are above v. So that's what you need to implement when you want to implement a domain. And there are many ways to do this. 2 very popular ones is use bit vectors and sparse sets. And what we're going to talk about is the sparse set, because they can illustrate very nicely some of the key features of these implementation. Initially, I'm just going to assume that the lower bound of the set is 0, so it's going to be a set between 0 and a value n. And so that's the values of the domains are going to be in that range. All right, so this is the way we represent a domain, and we're using a sparse set. And I need to go and explain to you a little bit what is going on here. So we are using 2 arrays, values and index, and a particular value here, size, okay, an integer size. Size represents the size of the domain, and value represent all the values which can be in the domain. So all the values which can be in the domains are going to be in this array. All right, so, and obviously currently everything is inside the domain, but then the size is going to move and remove some of these values. Okay, so you're going to see that. If I remove a value, the size is going to be, is going to be 8 instead of 9, and then 7, and so on and so forth. Now this index array is interesting. It's telling you where a particular value is located in the array value. So if I have a value 3 and I want to find where it's located, I'm going to ask the index array, hey, where is 3 located? Hey, tell me. And it's going to tell you, hey, it's in position 3. And then you will find the values in that particular position in this array value. Okay? So initially it's completely trivial, right? So they are located in exactly the position where they should be naturally. So that it's not actually anything fancy. But afterwards, the only guarantee that we will have is that if I have a value, if I want to find out the value v, I will query the index array. It will tell me where it is in the value array, and at that particular location, you can be sure that we will find the value v. That's the property that we maintain at all times. Okay. Now this is going to become clear as I start doing modification to this array. So let's do a first modification, which removes the value 4 from the array. So I want to remove this value there. Okay. So what am I going to do? I'm going to take 4 and I'm going to swap it with the last value inside the array. Boom. Okay. So I'm doing that. And now, once again, you can see all the values in my domain are still in the array value. I just have changed the position. Obviously, if you change the position, you have to change the index array, right? So we want that, the position of 8 has to become this one, the position of 4 has to become that one. So we want basically to be able to say that, hey, no, 8 is located here and 4 is located there, okay? So we have to change these 2 values, obviously, and we replace that by the correct value in the array. So you can see that 8 now is in position 4 of the array, and that 4 is in position 8 of the array. Now I still haven't removed the value 4. To do that, I just have to move the size by, to the left by 1 position, right? And now what is nice here is that this is the value which are in the array, and 4 is not inside the array. So inside my sparse set, I have the value 0, 1, 2, 3, 8, 5, 6, and 7, and the value 4 has been removed. Okay. Now all the values are still there, but this size, this size element there, this size component there, is telling me which are inside the set and which are not. Okay, so that's cute, right? So really cute. Now, once again, I've removed this value very efficiently. I have only used 5 operations. So in computer science term, this is constant time. This is good. So every time you will see, I will remove a value or assign a value in this set. I will only do a finite number of operation. Okay. Now I have a question for you. So how do I find if a value v is in the set? Okay, so let's go back here. You see this? Okay, so these are all the values which are in the set. This is not in the set. So how do I do that? How do I find out? How do I query this? How do I implement the method which tells me if a value is in the set? It's actually pretty simple. What you do is you take the value that you're interested in, you get its index, and if its index is on the left of this size value, there, this size bar, then it is in the array, otherwise it's not, right? So if I go back here, right, if my value here is telling me that I'm in position 4, obviously that's, smaller than 8, and, than 8, which is the size of my array, and therefore my value is inside the array. If I'm trying to see if the value 4 is present, the index is telling me 8, which basically means that the value is not in the array because it has to be strictly smaller than the size. All right? So I can test very quickly if a variable is inside the array. I just take the index and see if it's strictly smaller than the size. If it's strictly smaller than the size, it is in the array, otherwise it's not. Right? Once again, very, very quick. Okay, now let's remove 6 from the array, so I have 6 there, and I'm going to play exactly the same tricks as we have done. We are going to swap it with the last value in the array. Boom, right? Now I have this last position. I have obviously to change the indices, the index array. Boom, I change that. I remove this value, put them at the right place. Now I know that 6 is located in position 7, and 7 is located in position 6. I move the size, boom. Okay, now the values which are in my array are 0, 1, 2, 3, 5, 7, and 8. I have removed 4 and 6. If I try to see if 4 is inside the array, this is 8. The size of my array is 7. Obviously, it's not there. If I'm trying to see if 7 is inside the array, it's in position 6, which is smaller than 7, and therefore, the value 6 is inside the array. The value 7 is inside the array. Nice, okay? Now, once again, these are the values which are inside the set. These are the values which are removed. The left of size, you are in the set. Right, you are removed. Nice. Okay. Now, assume that I want to remove everything but 3. The only value that I want to leave inside the domain is the value 3. Can I do that? Can I do that? Yes, I can. So I'm going to take 3 now, and I'm going to put where am I going to put it? I'm going to put it inside in the first position of the array. So I'm swapping 3 with the first position. Boom. Okay. Obviously now I have to update the indices. Okay. And now you can see the value 3 now is in position 0. The value 0 is in position 3. And then what I have to do is change size. And in one step move it to the value 1. And therefore there is only one value inside the domain. And this is in position 0. Okay, so this value is inside the set and nothing else is inside the set. Beautiful, right? And once again, this takes constant time. This takes 5 operations to do. And that's what we have in the array. Now, how do we compute all these operations? Can we find easily if the value v is inside the domain? Yes, I've told you already how to do this. You simply look if the value is in a position which is smaller than the size. Can we find the size easily? Yes, obviously, because I keep the size all the time. Now, finding the min and the max is a little bit more complicated. You have to scan the array. But I'll show you one way to actually speed that up in a moment. Okay? Now, why did I do all these complicated things to represent a set? Why the hell did I do that? Okay? Is it just to torture you? Of course not. Okay, so the key point is that the propagation is actually changing the domain. So when you go down the tree and make some choices, you are changing the domains. But if there is no solution, if you fail, you're going to have to go back up. You have to backtrack and go back and restore the value in the domain. So you have a set, a domain, as both to be able to remove value from the domain, but it has also to have the ability to restore previous state of the domain efficiently, because otherwise you would not be able to go back up in the state, backtrack, and try different choices. So all the complexity that I'm showing you here for representing the set is motivated by the fact that we need to be able to restore domains very quickly. So how do we do that? When you have a sparse set, you can restore the domain by storing very, very little information. The only real thing that you need to save, from what I have shown you so far, is the size of the domain. Why? Because all the values still remain in the array value, right? So the only thing that I have done is that, hey, some of the value at the left of size are inside the domain. The value at the right, they are not in the domain. Now, if I want to restore, I can just, move the size, value there, the size of the domain. Now, the value may be at completely different positions, but they are still in the array, so it's going to work. Okay, so let me show you this. Okay, so I removed the value 4 here. So these values are in the set, and obviously 4 is not in the set. But assume that I want to restore, undo the fact that I have removed 4. I want to restore 4 in the domain because I made a choice, but the propagation failed. No, I have to restore the domain as they were before I made that choice. Can I do that efficiently? Yes, I can. The only thing that I need to do is move size over there. Now, all these values are in the set, right? No, they are in different position, right? So you see that 4 is now in position 8, and 8 is in position 4. But who cares, right? So all the values are inside the domain, and I can find them very, very quickly, right? So this is the beauty of these sparse sets. They are actually, you can remove value very fast, you can remove all the value but one very fast, and you can also restore, undo the operations that you just did. And the one before, obviously, as well. Okay, you can just remove the size value there, the size of the array, and then you restore this, exactly the set as it was before. Isn't this really, really cute? Is the dark side really, really cute sometimes? All right, so that's what I wanted to tell you. Now, I want to show you the implementation next time, okay, and in the next video, but you have the basic principle of what we want to implement. See you soon.